Now, how can we find the reward when the machine is a particular state? This Q1 tells that if the machine currently is in state 1, then in the next time period, the average earning will be this one. So 1 actually is calculated by multiplying this one with this one with this, and this one with this. So the formula for Q should be very simple, right? Q1 adamant product. Then we need to multiply with a column vector. Column vector will simply sum the elements of it. So by this way we can calculate this one. Any questions here? If you understand this, fine. If you do not understand this, you can later understand. Just assume that this is the probability of transition when the machine is in policy 1. This is the probability transition matrix when the machine is using policy 2, and so on. And the rewards for specific policies are this one. And then actually the expected earning in one transition is P1, P2, and P3 for policy 1, policy 2, and policy 3. Once we have this one, the algorithm starts. What is the purpose of this algorithm? The algorithm aims to find out what? Vn. What is Vn? Here I is the expected reward in n transition. Expected reward in n transition. And what is the formula for this one? Can anyone recall? It is Qi plus j equal to 1 to n Ij policy t n minus 1 and this one actually is the, so we can calculate this one. Now when we add the policy here, N I, actually D should be here. I missed this one. Then this Q1 will come with B, and here we will have B, and this one will be J. So in the first step, what the algorithm does is we start with V0. Zero is for what? Zero actually is equal to 0 for still I. And we set it to 0 for all I in 1 to 10. For all steps, 0 is set to 0. Then from here we actually move from V0 to V1 to V2. In this way we move on to, right? And V0 is equal to, what will be V1? V1 will be from this formula, it will be, if you consider a policy is there, say D is there, V1D, it will be equal to Ui D plus what? J equal to 1 to n E I J D, then V0. Let us start here. Start is the optimum one. We will calculate this one. So this equation, let me write it again in a fresh equation is V1 I will be Q I E plus J equal to 1 to n I J for policy B, then V0 So this is the equation. Now, since we assume that V naught is 0 for all states, so this part for now is gone. Then we can write V1 IV is equal to Vy. Or in the matrix form, what we can write? V1 when V is a vector for policy D is equal to. This is important. In a matrix form, what we can vector form we can write is V1 IV. That means for each step we will have one value. So we will consider the vector V1 and QIV for each step there will be a value. We will consider V1. Now, when D equal to 1, say what will be V11? V11 will be in the first iteration or here in the first stage. What will be the reward for policy 1? We write that this will be Q1. What is Q1? 1.4, 0.2 minus 1.4, 0.2 minus. Right? But then, if we want to write V1 for policy 2, it will be U. U2 is what? 1.4, 0.5 minus 1.4, 0.5 minus. And V13 will be equal to U3. What is U3? Here, 1.41 minus 1.41. At this point, if you write a computer program, then doing this matrix operation is difficult. But if you actually are doing manually, then what you can do, you can create a matrix V1, which actually is the column 1 here, column 2 here, column 2 here. What is that? 1.4, 0.2 minus 1.4, 0.5 minus 1.4, 1 minus. From here, actually what we want to calculate, we want to calculate this one. What is this? This one is V1 star. V1 star indicates if you start in state 1, this is state 1, then when we use policy 1, the reward is this. When we use policy 2, then the reward is this. When we use policy 3, then the reward is this. So this V1 star indicates maximum reward for any policies. Maybe here maximum will be what? 1.4. And V star, this one will be the policy that generates the maximum reward. Which policy? Since all 1, 2, 3, all three policies have the same value. So V star has a value for state 1 is 1, 2, 3. Now we will do what? State 2 here, then the reward is 0.2, reward is 0.5, reward is 1. What is the maximum value? 1. And which actually policy here is generating this one? And the bottom row, it is 2. Here, 1, 2, 3. Actually, in matrix form, this V1 star has a manual function. You can write this max. Within the max, if you have the vector V1, and then you get, if you pass the parameter 2, then what it does, it returns the maximum value of the columns. For this matrix, the maximum value is 1, 4. Maximum value of this column is column wise 1.4, 1.4, 1.4. What is the maximum value? 1. 0.2, 0.2, 0.5, 1. So for each row, it finds the maximum value among the columns. So you can find this operation here by yourself. So what we have, we calculated this one. Now, if we move on to this one, V3, for policy 1, what it will be? It will be Q1 plus we will need this operation, right? We will need this operation. This operation is what? So here what is we are doing? If this is the probability transition matrix, then P11, and if we have this vector here, En minus 1, 1, then actually this one is multiplied with this one is multiplied with this one is multiplied with this one, and then added together. So what we can write instead of this summation can be replaced by the vector operation, the transition probability matrix, policy 1, and then the optimum one, the n minus 1, which actually here it is 1. So we can write E1 plus E1. If we write this one, then it will be, what is the value of E1? 1.4, 0.2 minus 2, right? 0.2 minus 2 plus, what is the value of P1? I have it is 0.6, 0.3, 0.1, this is 0, 0.5, 0.5, then 1, 0. And what is the optimum value here? We have just found the optimum value here. 1.4, 1 minus 1.4, 1 minus 2. Now, if we calculate this one, the first one remains same, 1.4, 0.2, minus 2. Now, this one actually, if you consider this one for I is equal to 1, then actually what it is doing? P11 is multiplied with this one, P12 is multiplied with this one, P12 is multiplied with this one. The matrix operation, matrix product is doing the very same thing. And here, this multiplication will result in a value which is 0.94 minus 0.5, 1.4. This actually results in 1.4, 0.94 is equal to 2.34. 0.2 minus 0.5, it will be Now, there is a distance here. I don't know who is on it. According to me, it is 0.3, and this one is minus 0.6. Actually, it is 0.3 or 0.5 or 0 doesn't matter, because when you calculate this one and this one, then the maximum will be for this row, this one, maximum for this row is this one, maximum for this row is this one. Similarly, we can find out this one. Okay, so by this way, we can calculate this one. Third step does the same thing. Fourth step, the final one, it is the value of that fourth iteration. Since it should be V2, not V2i, it should be V4i. See? V1, this is V2, this should be V3, and this should be V4. So please don't follow this one, who give the exact values, learn the policies. So from here we can see that the optimal solution shows that the user should do nothing when the equipment is moving anywhere, replace the equipment if it is acceptable area, and replace the dead condition. So do nothing, replace and replace. But I think since we have a wrong value here, the result should be totally different if you go with the correct value. Then doesn't matter here. So, and ultimately we say that if we start in stage 1, then after 4 stages, the optimal profit will be 4.5, and whatever policy we use, it remains same. Then if we start in stage 2, after 4 stages, the optimal reward will be this one, and this will happen only when we use the policy 3. And for if we start in stage 3, the optimal reward will be this one. So you can see here actually we have a little different thing. It is getting higher one because we are overrolling this one, but the value calculated here are not what we should expect. Okay. What is the mistakes? are mistakes in the solution. So I will request please do it with the correct solution and take it to. So that next year if I teach this course. Now before we move from here, the main thing is that in the vector operation, what we do V2 Vn is equal to, we have written here QV plus PE multiplied by Pn minus 1. This gives you the first column. How can we create the matrix Pn? That R operation like this, Pn1, Pn2, Pn2. So you can make a matrix. Once you have a matrix, then you can calculate the optimum value by using max. Argument will be the matrix itself, and the matrix column wise you will put 2, and then P star you can invent an operation like argmax. Then what it will return? It will return the column number that produces the maximum value. So once you have this one, the nth state is there, then you can move on. One thing still remaining, that is V not equal to 0. V not equal to, when you have V not equal to 0 vector, then it immediately produces V1 equal to V1 for any. V1 will be. Any question here? Very simple. We'll discuss this one from the last classes. Now, the policy iteration method. Before we move on to the example, we'll move on to the example and we'll try to finish it as soon as we can. Right? That is what is our primary objective. What is the difference between the policy iteration and the value iteration? That will be the first understanding. In case of a value iteration method, we have a finite horizon. That is, number of stages the microprocessor will move on is finite, 5, 10, 100, 200. And in case of policy iteration, we consider infinite horizon. That means the chain itself is forever. Now, what we need to do when we go for the policy iteration method, since it is moving from 1, 2, 3, it is never stopping, then when you calculate the Pn, optimum Pn, for n states, there are 2 cases. In one case, what we consider a discounting is there. If discounting is not here, how can you calculate the n escape condition probabilities? In case of the value iteration, the n escape condition probability calculation is easier because you start and then you calculate. But the system that is running forever, how can you calculate n escape condition probabilities? There is no starting point, there is no ending point. So either there is a discounting factor. When there is a discounting factor, what happens? When you have a value V0, the value V0 when moves on to V1, actually it is discounted by a factor beta. When the V1 moves on to V2, it is discounted by a factor beta. Now, this V0 is included in V1. And now in V2, V0 included as with a discount beta. What is the discount for V0 here in V2? Is the question clear? For example, we have 3 steps. Step 0, step 1, step 2. Here you have 100 taka. When you move this 100 taka into step 1, Then since you are only considering 90% says beta equal to 0.9, then this 100 comes here as plus whatever you have here. Now when this one is coming here, a discounting of the vector of beta is seen. So this 90 will go through another discounting. So in this state actually, this discounting for the first one will be beta square. Now if we have n steps, the first one actually will come after n steps, then it will be reduced by a factor beta to the power. Second one will be reduced by a factor beta to the power n minus 1. Right? In this way, the discounting will actually reduce the impact of this one. That's why actually we can calculate this optimum value when discounting is there. Now, when discounting is not there, values are going. But how can we calculate? Because we are starting at a certain point and we want to calculate for it. In that case, what we do? The second method is actually we move on to expected value. That is a long-term expected. What we call the steady state value. Now, instead of considering the transition probability of the matrix, what we do? We actually calculate what is pi? Pi is the steady state probability. This steady state probability filter can be calculated for a Markov chain which is R. And it gives us the fraction of time the chain will visit a particular step, and it also gives us the two things. One is long-term fraction, it will visit, and the fraction of time in hour of time the chain will be in a particular step. All are there. So this one, the policy iteration method, actually we have two processes. In one, either we consider the discounting. In another one, we do not consider discounting. In that case, actually, we need to consider the steady state probability vector. So we calculated this one based on the long-term probability vector pi, and when this one comes in, what we do? The equation remains same. This is the equation for the n step. N step reward. And for algorithm Markov chain, the stationary tendency actually is now. So we need to focus this equation actually says this one is converted to this one. What is the difference here? The difference is we define a new term. What is T? It's called the gain of the system. The gain of the system actually is defined as the long-term average reward that the process can obtain when there will be one step transition. Previously, we calculated the one step transition by this way. The transition probability and the reward. Now this one actually is further multiplied with the long-term probability vector, and then we get the value of G. So this one G is I multiplied by phi I. So we get G. And once we have the G, then this equation or the policy iteration method becomes a system of simultaneous linear equation. GB plus BI plus EYT plus this one. For this I, we will have a one equation. once we have n equations, solving the equations will give us the values of vi. But how many unknowns are here? In this equation, we have one unknown vi, this one, and we have one more unknown. So n plus one unknowns are there. That's why the solution that the book assumes is that setting this one equal to 0. We always will set n equal to 0, and the values will be calculated relative to this one. You can have many values for this one because since you have n plus one unknown, you can always assume one value for one unknown, and that will give you the values of the simultaneous solution will give you the values of the n unknowns. So values the book consider that will set the last variable 0, and all the values will be in that case relative to the value n equal to 0. If this changes, all the values will be 0. And once we have the system of linear equation, then the policy iteration method works in one step. We solve the system of linear equation here, as I mentioned, and then based on that, we find the policy improvement, which policy is producing the best result by calculating this. So in this iteration, what we do, we calculate the value of V1 to Vn, where we assume G equal to 0 and 1 is G is calculated, G is for the gain of the system. So we calculated this one, we assume this one equal to 0, and in the first step we call it is the value determination step. And in the policy improvement rule, what we do, we calculate this one for each step, and once we calculate it for each step, we find out for a particular step which policy is giving the maximum value of this one, and in that way we find for each step the optimum policy. So it becomes the new policy for the next step. So what in the stopping rule is there? The stopping rule says we will be as an example, it will be very clear. What we do when in two successive iterations the policy remains same, we say the algorithm converges. So first let us jump. A very simple example. We have a Markov chain V1, it is an algorithm Markov chain. The Markov chain, you can draw the solving diagram. 1, step 2 is here. Transition probability is 0.6, 1 to 1 is 0.4, and 2 to 1 is 0.2, and 2 to 2 is 0.8. When there is a transition from 1 to 2, the reward is 4. When the transition is from 1 to 1, the reward is 4. When the transition from 2 to 1, reward is -2. And 2 to 2, the reward is 0. Now, for this Markov chain, what is actually, we need to find out the best policy that should actually be used for the optimum operation of the Markov decision process. And we will be using both the two methods. One is that I mentioned here. One with the discounting, another one actually will be using Z, the long-term gain. So let's start with the gain one. What it does, it finds a system of n linear equation. What is the linear equation? Let me write it here. Z plus Vi equal to Ey, then plus J equal to 1 to n Bij. And so this is the system of linear equations. We will have n equations for by varying I. Question is, what will be the value of B? P for this system of radial equation, what we will do at the first iteration, we will issue an arbitrary. For example, following the text, we will issue P is equal to 1. That means we are using policy 1 for both the coexistence. That means we will be using this one, we will be using this one, we will be using this one. So this is this one. Others, when we go to the other direction, what will be? For the other step, the D will be the optimum. How can we calculate the optimum? We will see. So the first equation will be what? When actually I equal to 1, our equation will be G plus D1 equal to how to write it? D1, okay? Equal to D1 1 plus this one is D11 into D1 plus D12 into. So we understand this one. The same thing is written here, and I means the policies. What will be the second equation? The second equation will be for G plus V2 equal to P1. Sorry, P1 plus E, since J is equal to 2, I is equal to 2, I is equal to 2 means this is 2 1, then policy 1, this is 1 plus 2 1. Did I write things? G V1 V1 1. Okay. So once we have this one, then we need to solve this one. Before solving this one, let us first write the values. What is the value? Q1 is what? Q11 and Q21. For policy 1, this is Q11 and this is going to Q21. This 1 and 2 indicates the policy 1, row 1 is policy 1, row. So the first one will be 6.4, the second one will be 1. Now, as I mentioned, we will always assume in solving the system A equal to 0. So we do not have this part. Since we do not have this part, then the equation becomes G plus D1 equal to D11 is 6.4 plus what is P11? P11 is 1.4 into D1 is the variable that we need to find out. For the second equation, it will be G equal to minus 0.4 plus this probability is P12, this is 0.2 into. So up to this point, whether we are okay or not. Just please follow. What we do, like the previous one in value reduction method, we have the same equation. This one. Now, why the equation has been changed? The equation has been changed because we are considering a situation where on the infinite horizon, it is running forever. Now, when this chain is running forever, and you need to calculate the gain in n step, then how do you calculate it? To calculate this one, we calculate everything. The key is giving us the gain of the system. If there is a single transition, what is the long-term gain? And based on that, if we want to calculate Dn, forget about the policy or not, then it will be Ng. That means the gain in transition, and it should be added with the starting one. Or yes, no. This is the ultimate solution. And we are not going to the detailed math. Following the text, what we are considering here, the solution to this one becomes now a system of linear equation. How many equations are there? 8 equations. What is the system of linear equation? If this is the matrix, then first we need to choose a policy. At the beginning, we start with either policy 1 or policy 2. Let's say, following the book, we start with the policy 1. Once we start the policy 1, then the system of linear equation becomes what is this? G is the gain, here is the for node I, and this is J is for all the nodes. This is the derivation probability, and this is Qi. Qi is from here. What is it? It is the reward. For Qi, we are writing Qi. This is for state 1, this is for state 2. So now we need to write the equations. So when I equal to 1, then this becomes the equation for state 1. When I equal to 2, then this becomes the. So besides the values of G, we have the starting, or we have the actually reward for node 1 and node 2, or state 1 and state 2. How would we write G plus reward, G plus B? This is common. Then here Qi, actually Qi is the, okay, we will consider Q. This is the vector, and it is the policy. Now for this one actually becomes Q1, 1. That means for policy 1, state 1. This one becomes Q2, 1. That is for policy 1, state 2. So here we will have Q1, 1. Here we will have Q2. Similarly, this according to this equation, when we are adding for state I, then there will be transition from I to I, j equal to 1, and this one will be for node I, plus from I to j, 1 to 2, policy 1, node 2. Similarly, for I equal to 2, we can write this is 2 to 1, then 2 to 2, and V1. Second thing is that we need to assume that Vn equal to j. Why do we assume that? Since we have n plus 1 unknowns, we need to solve the system of linear equations with n equation, then we need to assume a value for this one. And once we have the n equal to 0, then this part of the equation actually is gone. Once this is gone, then the equations actually are becoming this one. G plus D1 equal to 6.4 plus 0.4 D1, which we can write as G plus 1 minus 0.4 D1 equal to 6.4, and the second one is G plus G minus 0.2 D1 equal to minus 0.4. Now, since we have now two variables only, we can solve it. Following the text, here is the solution. D1 is equal to 8.5, D2 is equal to 0, as we assume. Is equal to 100. Here is matrix version of this one. If you want to, then we can actually, since you prefer the matrix version, in the exam I found that most of the students prefer the matrix version. I need to actually then find what will be the matrix version. So in case of the matrix version, how can we write this system of linear equation? The system of linear equation will be identity matrix E multiplied with probability. Is equal to what? V1, Vn. This one will be equal to, what is the equation? RD. No, this is not RD. RD is a matrix. We need to have here minus G multiplied by bar. So if we apply this one here, what will be? Let's say our is a matrix here. Let us write here identity matrix minus dilution probability matrix for policy B will be multiplied by what? The vector B equal to QB minus GC. If we write it, what will be the identity matrix? What will be the dimension of the identity matrix? 1 by 2 by 0. What is the P vector? Since we are assuming the policy 1, then it will be 0.4, 0.6, 0.2, 0.8 multiplied by P1. Okay, we need this one, right? Equal to what is Q here? 6.4 minus 0.4. Minus what? What is the G? G is a variable, and we have a column vector with all one. If we do this operation, let's say go here. 1 minus 4 becomes 0.6, then 0 minus 6 becomes minus 6, 0 minus 2 becomes minus 0.2, 1 minus 8 becomes 0.2. Multiplied by P1, P2 equal to what? What is this? 6.4 minus C minus 4 minus 0. So we understand this, and now we have two equations here. What are the equations? If we write the equations here, if we write the equations here, the first equation will be 0.6 V1 minus 0.6 V2 plus G equal to 6.4. The second equation will be minus 0.2 V1 plus 0.2 V2 plus G equal to minus 0.4. Just if you look at the equations, you find that G plus 1 minus 0.6 V1 equal to 0.6, 6.4, 0.6 V1. And when we put actually V2 equal to 0, then this part further vanishes and the equation becomes 0.6 V1 plus G, therefore 0.6 V1 plus G equal to 6.4 minus 0.2 V1 plus G equal to. So, if we have this matrix operation, what is the matrix operation? Then we will have a system of linear equation in the matrix multiplied by vector V1 V2 equal to a vector. So what we need to calculate? The solution. Either way, you can do it. Once you calculate this one, the value of V1 and G and V2 will be available. The second step is time is up, right? Let me finish this one. Once we have this one, the second step is we need to actually find out the optimum value for this optimum value for this one. Now what we have for a particular policy, we have the values of V1 and we know the value of V1 here, and this dimension probability matrix is given to us. This thing is done here. When D is equal to 1, then P1 is equal to 6.4, P11 is 0.4, P12 is, since U is equal to 0, we do not have this part, so P11 is multiplied by P1, and the value becomes 9.8, this value becomes 1.2, this is 11.2, what we will see for a particular step what is the maximum. The maximum value is this one. We will calculate what policy is giving us this value. But this one, this is the maximum value. So, if even though we started with policy now we find that for both states, the policy actually is, if we move on to the next step, a matrix resolution is available here as well. We move on to the next step, the matrix become U is this one, G is this one, and we find that still this one is better than this one is better than this, so policy is. So we conclude that policy 2 is the ultimate policy for this system. And the input policy is policy 2 for both state 1 and 2. And we can calculate the thing of G is in this one. And once we have this one, then for any step, we can calculate the addition of it. So here we have V1, V1 has a value, and V2 has a value right here. Then we can calculate the extension for any step. Okay, for now we stop here. We'll go to this class, right? With you.